cycle MIPS processor. It has a control unit split into two parts, main control and ALU control. It has a instruction fetch unit, and it has the part of the data path where the computations will take place. Data will be fetched and calculated and stored. Eventually, all our data will either come from here or come from here and be stored here or be stored here. So we're processing data here under the control of the control unit. So this is kind of the summary of it. You can see that the control unit is going to need to produce all of the blue signals which do the controlling. We call those data points or control points. I'm sorry, control signals or control points. And these are coming out of here. So regdest, ALU source, etc. Find their usages, as you can see, in the data path. So that's what we came to last time. Now what we're going to do is analyze the timing of this single cycle processor for the worst case instruction. The worst case instruction is the load instruction. If we go back real quick, you'll see why. Load requires us to fetch the instruction, bring it into its fields. Its fields will cause a register value and an immediate value to end up being added here to create an address. The address will go to data memory. Data memory will produce the result that we're reading. It'll go through this MUX and come back here and be written into register. So we start at register, we go through data memory, we end up back at register. The slowest instruction will be the load word instruction. Let's see what the timing about the load word instruction looks like. On the falling edge of the clock, the PC receives a new value. Clock to Q is the delay of every register. So from the clocking edge until the new value appears on the Q outputs is some finite delay. So that's our first delay, changing the value of PC. That new value of PC will be sent to the instruction memory and will cause us to fetch our instruction. How long does that take? Well, instruction memories don't have zero access time. In fact, they have finite access time. So the instruction memory access time from the beginning of the time when the new PC value is valid until here gives us our second delay. Now that we have our new instruction value, that means we have new values of RS, RT, RD, op, and func, because those are the values that come out with the instruction field. So because we have new values of those, this bus changes at this point, and those values, namely the instruction itself, you need the codes in the fields in the instruction, can go somewhere and do something. Well, where they go through is the delay through the control logic is particularly for the op field to tell us what are we doing. Oh, it's a load word is known right here. It's not known right here because the instruction with some bits is known here, but control logic has to tell us what we have to do. In addition to that, at this time right here, the register file is sent the value of RS and RT, and so there's a delay through the register file. Register file is a miniature memory, you might say. It has an access time. So register file access time tells us new values of RS and RT at that point right here. On bus A, let's go see what bus A is. Okay, the value of RS. So that value is known and goes to the ALU at that time. So we fetched a value. RT doesn't matter, of course, as you know. So at that time, we have a new value at the entrance of the ALU. In addition to that, as you can see here, we're also, from this point here, having a slight delay for the delay through the extender and the MUX for the immediate field. So the immediate field shows up, as you can see here, sooner than the RS field. And now we can add them together in the ALU. But the ALU delay is not zero either. So now we have an ALU delay to add the sum of those two together. What does that produce? Makes our address. Now we have the memory address. Wow. From here all the way here just to create the memory address. Well, you can see why. There's a set of sequential combinational delays here in sequence, R to R to. Now that we've got a new ALU value on the output, that add value is the address that goes to the data memory. So you can see that starting at that point in time, there's a delay in order to get the new value in the data memory. So that's called the data memory access time. Given an address, do you get the value immediately that you're trying to read? No, of course not. You must wait. And so the data memory's delay time brings us to right here. Now that we have the value coming out from the data memory, that's the thing we want to write back into the register file, isn't it? It's a load word instruction. So we've got something from data memory. We want to put it back in the register file. And so it's available right here. Finally, on bus W, a new value is available. And you can see that bus W is in fact this bus right here. So after it gets out of the data memory and through the MUX, we have a value available here. This value has to be here and stable before the clock comes by a certain amount of time that we call setup time, or hold time, excuse me. It has to be called the hold time. So that means that, in fact, this margin here has to be greater than 0, or it won't be there in time, because here's the falling edge of the clock, which triggers the load into the register file. And in fact, there's a factor missing called clock skew. So if we begin to look at this, we'll notice that the load instruction is the worst case delay. It has a very long cycle time because it's the sum of the clock to queue delay for the PC, followed by the instruction memory access time, followed by the register file access time, followed by the ALU delay time, followed by the data memory access time, and then we still have to be there ahead of the setup time for the register file, and we have to take into account clock skew. So the sum of all those is my minimum clock cycle. If I clock it faster than that, I guarantee I won't be writing the correct value into the register file at the end of a load instruction. It'll be too fast. So I'm limited by these delays. Okay, that's my worst case. Now, if you have a single cycle processor, what does that mean? Every instruction executes in one cycle. That means the clock cycle which we determined for the slowest instruction will be the clock cycle for every instruction. We can't have a variable clock cycle that says, go short for this one, go long for this one, short for that. You can't have a clock cycle that varies. The clock is, as you know, on a regular timing pulse, and so therefore the edges of the clock will have a fixed separation in time. It's not going to be variable. Oh, what instruction is it? Speed it up, slow it down, speed it up, slow it down. The clock rate is like a heart rate. It's a regular rhythm. So therefore, in order to do this instruction, it has to be that slow. Therefore, that's going to be the clock cycle time for all instructions. So therefore, what we're going to have is single cycle machine's advantage is the logic and the clocking are very simple, and we get a CPI of 1. That's great. But the disadvantage is we get a very long clock cycle. Very long clock cycle. In fact, unnecessarily long. Long enough for load is too long for add, too long for store, too long for branch, too long for jump, too long for all the others. Don't need to be that long, but it has to be that long because it has to be a constant clock cycle. So therefore, we get the worst case delay and a very long clock cycle time. That's one major disadvantage. And the second one is that we get inefficient utilization of our resources because we've got the memory and functional units and register file, and they all take different lengths of time to use them, but we only use them once during a instruction. So because they're only used once per clock cycle, for example, our ALU, which is a big piece of hardware, sits empty and idle most of the time. Only a very small amount of the time is our ALU used, or our data memory used, or our multiplexers used, or our register file used. Only a very small percentage of the clock time. So you have this resource you've paid for in transistors, and you're not using it. That's the second big disadvantage. And so the result is, for single cycle architectures, all machines would have a CPI of 1, and their clock cycle time would just be set by whatever their longest instruction is. And so if you can remember, performance, which is really related to time, is equal to, remember the equation? Number of instructions multiplied by CPI multiplied by clock cycle time. And we've just said this is 1 and this is big and this is not related to the implementation. And so this is fixed and this is fixed and this is going to be as long as the longest has to make it. So we don't get very good performance from single cycle processors, but we at least have done an analysis to see what we would get. So let's summarize now our single cycle processor. Our data path will be CPI of 1 with a long clock cycle time. There's 5 steps to designing a processor. We've taken it through these steps. The first 3 were for the data path. The second 2 were for the control unit. You've actually watched the design of a processor take place here on the slides in the last couple of hours as we walk through these steps. If you don't believe it, go back and check the slides and you'll see that's what we did first, that's what we did second, that's what we did third, that's what we did fourth, that's what we did fifth. Control turned out to be a lot harder than the data path. As you know, we did this first and then this, and we saw the control was a lot more challenging. And yet MIPS makes control easy compared to other architectures because the instructions all have the same size. In Intel, as you remember, they don't have the same size at all. The source registers are always in the same location. That's not true of many architectures. We know where we're going to find RS and RT. The immediates are always the same size, always in the same location. Last 16 bits of the I-type. That's not the case in all architectures at all. And the operations are always on registers or immediates, never on memory values. We do not have operations on memory values. We don't touch memory values except to bring them in, and then we operate on them. So that also makes the machine much, much simpler to design the control of. Machines that do this, that only operate on register values or immediates and don't operate on memory values, are called load-store machines. Load-store architecture, because all you ever do with memory is you either load or you store. You don't ever operate on things in memory values. You first bring them in and you operate them when they're in the processor. Okay, so that's our summary of single cycle processor architecture. Are there any questions about it? All right, I think you probably know where I'm going to go if you've looked ahead in the chapter at all. Since we've said, well, there's single cycle, it's not that great. You can imagine what we're going to do now is move to an advanced architecture and build on this foundation, but go forward to get higher performance. How do you think we're going to get higher performance? Reduce this to less than 1? Probably not. Reduce this? Yeah. How are we going to make that faster? Well, after the commercial break, don't change channels. Come back and you'll see. All right, what we're going to do is we're going to pipeline our architecture, and that's what we're going to do in the next slide. Okay, first let's do a kind of a review of single cycle to make sure we've got it. All right, you're going to do a design project that begins with a single cycle and moves it up to pipelining. So you're going to actually do what we're going to do right now. You're going to pipeline a single cycle architecture. And so I'd like to make sure that we all understand how to do it. Okay, here's our single cycle architecture with the control unit. Notice control is split in two parts, main control and ALU control. We've done just what we designed before. And control's in red and the data path is in black. What's this stuff up here on top? What's all that? Branching stuff, right? It's obviously branching stuff. It's not, here's our instruction memory. So obviously PC's here for fetching, but it's also for computing the next PC. So obviously that allows us to either add 4 and take it, or add 4 and then add something else, which comes from sign extended immediate. So that's obviously our branching. So this is for the branching, computing the next address and writing it into the PC. Don't have jumping up there yet. Here's our classic data path for stores and loads and arithmetic operations and logical operations. And here's our control units. Okay, there we go. Now, let's notice that when we do an R-type instruction, what's active and what's not active. For an R-type instruction, the dark blue lines are active data paths, and the circled red are active control points. So let's make sure we understand what we're saying here. For an ALU operation, an R-type operation, we're just going to go to the next sequential address. We're not going to branch off to somewhere else. So that means that current value of PC plus 4 gets selected at the MUX, and that's what's going to be sent back around. So that makes sense. We're going to sequentially increment. So we circle that one. It also means that we're going to fetch 2 register operands out of here using the RS and RT values coming from the instruction. So here they go. Here's the 2 buses. And we'll send them to the ALU, which means we have to make sure we select this one through here. They'll be added, ANDed, ORed, whatever they are. It's an R-type in the ALU, and that's determined by the ALU control. It's going to send the code. If it's an R-type, then the code will come from here. If it's not an R-type, the code will come from here and just pass through. But if this says, hey, it's an R-type, then this one will know what R-type it needs to be and send the code. All right. The ALU op, as you see, is coming out of the control unit, coming around down here. In addition to ALU op, we need to know if it's an R-type, we need to know the function field. So notice that the last 6 bits here, which are 5, 4, 3, 2, 1, and 0, the function field is going here, as well as the ALU op coming out of here. So if it's R-type, this says it's R-type, look in your function field. If it's not R-type, this says I know what it is, listen to me, don't pay attention to him. Anyway, we know what the ALU will do. Okay, so the ALU is going to produce our result, and since it's an R-type, we don't have anything to do with memory, so our result needs to get through this multiplexer and back around and be written into the register file. So we take 2 register operands, and we end up writing a register result. Where do we write the register result? The answer is to the RD field. That'll be found on bits 15, 14, 13, 12, and 11. Right? Not RT. RT is found on bits 20, 19, 18, 17, and 16. So the bits with the least, the values that are the lowest in the instruction field are the RD field, that's the RT field, that's the RS field, right? So 2 sources, 1 destination. Any questions about how to read that schematic? Blue is where the data goes, red is where the control goes. Are we okay with that? Any questions about that at all for the R-type instructions? Okay, if you don't ask me questions, then you know how I am. I ask you questions. So I'm getting ready to ask you some questions. If you don't have any for me, it means you understand it. So then I'm going to turn it around and let you have your chance. No questions? Great. Good. I'm looking forward to this. Okay, now let's go to the load word instruction. And you'll notice that here I have not made blue and have not circled in red the active data and control paths because I'm going to take the pen and select the lucky victim and ask you to come up and circle them and highlight them yourself. Okay? Not on the screen. Okay? Now remember, our instruction is load word. And we just went through that with the timing pass. So if we're going to load a word, then some certain things have to happen. Can you show us what's going to happen? Load word. Okay, talk to them. Talk to them.
If you are going to load the word, you should first write to memory. Circle this.
Write to, okay. How many would like to agree with him that when we load a word, we write something into memory? Okay. All right. We're going to read from memory. So that means we're not going to circle this, right? Need a better pen? Try that one. Yeah. Okay, so we're going to read from memory. And where will it come out from when we read it?
It's come out from.
Yeah, so how's it going to get through that multiplexer? Yeah, how's it going to get through the multiplexer?
Through. Mem to rate. Yeah, I mean this one.
Yes, okay.
So it goes to right data.
So around to here. And how do we get it into here? Yeah, reg right. Anything else? Where will we write it? Where will we write it?
We write it to.
What will be the address of the destination?
Right address, of course. It's come from control unit.
Well, which one do I select? Do I want this bus, bits 20 through 16, or do I want this one, bits 15 through 11?
It's come from PC.
These are coming from the instruction. Okay, look, these are all instruction fields. Which field of the instruction do I want to put here?
Which field of the instruction? It depends on the instruction.
Yeah, well, this is a load instruction, so now we know. So it needs to be RS or RT or RD or op or func or shift. Which field do I put there? It's the destination address. He's deciding what the destination address should be for a load, aren't you? Yeah. Okay. All right. How does a load work? We have to remember it's register transfer language, don't we? What's the register transfer language for load? Who remembers? Get RS and add it to what? The sign extended immediate. And what did you form when you did that addition? The address of something to go to data memory. Great. Then that means that you use the op to decide that it's a load. You used RS and you used the immediate. What's left over in the I format? RT. So what is RT then? What RT is the destination address that we're going to put that value from memory into the register file. So which one of these two is RT? Is it bits 20, 19, 18, 17, and 16, or is it bits 15, 14, 13, 12, and 11? Yeah. Okay. Let me give you a better pen. Okay. All right. What else needs to be decided? Okay, there's another one here. Well, that's always sign extending. No problem there. What about ALU control? What are we doing with the ALU? What do we want the ALU to do in a load operation? Added, right? We want the ALU to add two things. Yeah? So make it add. Yeah, that matters. Okay.
And
Keep looking. Is there anything else there?
I can't see.
Okay. How about now what data paths are active? Use this and make them big and blue. Which data paths are active now? Where's the data flowing? He did control. He's right on the control. Now how about the data? Oh, wait, there's one missing. There's one missing. What are you going to do here? They'll use source. You have to choose. For the load operation, does he want to take the RT bus coming out of the register file, or does he want to take this sign extended immediate coming up from here? Which one does he want? Make it choose sign extended immediate then. Okay. Good. Okay. Now the data path, yeah.
First we read the data from memory.
First we read the data from memory? No.
No.
Actually, start back over here.
And we take the immediate value.
Yeah, where did the immediate value come from?
From sign extended.
No, it's right here. Here it is, 15 down to 0. Where did that come from? Where did that immediate value come from?
Instruction.
Yeah, the instruction. Make that blue. Okay, great. Okay. Is this important? Is this important here? No. Is this important? Yeah. Okay. So anything that's important. Okay. Is this important? RS is not important? Okay, RS is important. Okay, great. All right, fine. Is this important? What's 31, 30, 29, 28, 27, 26? What's that? Opcode field. Is that important? Does that need to go to the control unit? Yeah? Okay. Okay, fine. Good. Now, no, that's okay. All right, now what comes out of the register file? What comes out of the register file? You're giving an RS? So what are you going to get? He's given a 5-bit field here. 25, 24, 23, 22, and 21. That's the RS field. So what's he going to get when he reads this register file? The value of a register. Where's he going to get it? Is it going to be here, here, here? Where's he going to get it? Where's that value going to come out? Yeah, data 1. When you give an address here, for read address 1, you're going to get the data here, read data 1. So make that blue. Okay, that's his RS register value. It's going to the ALU. Is anything else going to the ALU? The sign extended immediate is going to the ALU, isn't it? Okay, let's get that blue. Okay, and now continue. Right, and then from there where? We're going to add those two together. What happens then? He's saying add these two, so please continue. What happens? Okay, where does it go? To the address of data memory, and then what happens then? And then we read it, and it comes out the read port, and then what does it do then? Comes around all the way up to here. Okay. That's okay. That's okay. All right. Now, did he leave out anything that's important? Yeah. What about getting the next PC to the right value? Does the PC value jump to a different address? No. What does it do? PC plus 4. So please make it do PC plus 4. Yeah. PC goes up to there, and they add 4, and it's added. Great. Okay. Oh, we forgot to choose one. Here, I've got to give you a red color here. Yeah, what do we do here at this MUX? What do we do with that MUX? Yeah, we're going to choose that one. That's right. Okay. Come on. Okay. Okay. Come on, stop. And, okay, we're done. Let's give him a hand. He did a good job. All right. Now we're going to do what teachers do. We're going to check your work. So watch this. The next slide actually has the the right answer. So I'd like everybody to see how well we did. Did we get it right? Did we miss anything? He got that one, he got that one, he got that one in the end. We got that one, got that one. We circled here, but that's okay, same idea. Yeah, blue paths. We get all the blue paths? Looks like we got it. Yeah, I think you got it 100% right. So you're headed for an A. Let's do the next one. Branch instruction. Okay, now how would branch be different? How would branch be different? Let's think about what does branch do. What's the RTL for a branch instruction? Take two registers, send them here, do what? Compare by doing what? Subtracting them. And that's finished for the data path. All we want to know is that FARC 0 or not? So we did all that work just to get this little signal here, and the rest of the activity happens up there because branches don't change any data or anything in memory. What do they change? PC. And they're either going to change it this way or change it that way. What are the two alternatives for changing the PC? Plus 4 or PC plus 4 plus sign extended immediate multiplied by 4. Remember all that? Sign extended immediate multiplied by 4. Okay, so those are the two choices. So the rest of the activity is going to happen up here. And we'll just let you think about it for a minute. How many of the things down here matter? How many matter? Does this matter? Does this matter or this matter? No, we're not writing anything back, are we? We are reading, though, so that means these matter, don't they? Our S and our T. That means these matter. That means this matters to get it here. That means we got to do something, so this matters and this matters, right? To do a subtraction. And after that, does any of this matter? No, 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 no. Okay, so we'll just be sending up the 0 signal. It'll be yes, they're equal, or no, they're not equal. That's our two possibilities coming out of our subtraction. Okay, let's see what happens here. So here's the answer. Obviously, they both matter here because it depends on the value of this signal here. It might be telling us take the sequential address plus 4. It might be telling us take the branch address. This creates the branch address. Obviously, all this is blue because we're calculating both possibilities and putting them right here on the two doors of the multiplexer to be chosen by the AND of, is it a branch instruction and are they equal? So if it's a branch and they're equal, then we take the branch. If not, then we don't. Okay, and what else was blue here? Well, obviously, these two guys are blue, and the sign extended immediate. The sign extended immediate isn't for here, but notice where else it goes. The sign extended immediate goes up here to be multiplied by 4, to be added to PC plus 4 to create the branch address. None of this matters. You don't see any circles over there, but we do need to, that matters, and that matters, and that matters. So we see how to control and execute a BEQ instruction. Any questions about this? Okay. Let's add jump. Well, the jump instruction wasn't there before. If you look close, you'll see what changed. Watch the top part. How many multiplexers? Add, then one mux. Add, then one mux, then another mux. So the new thing is this. And look what we've done. We've taken from here the 26-bit pseudo-direct address and brought it up here. We didn't have it before. Before, if you remember, it ended right here. Look again. Oops. Yeah, it just ends there. But now we're going to take this, which is our instruction, and we're going to peel off the lower 26 bits and send them up there, and we're going to shift them left by multiplying by 2, and then we're going to have a 28-bit. We're going to concatenate with the PC plus 4's highest 4 bits to make a 32-bit jump target address. And that jump target address, along with the sequential address, along with the branch address, becomes the 3 possibilities for the next value of the PC, next value of the instruction that I'll fetch. Okay, so how do you know if you take the jump or not? If you do the jump or not? How do you know if you take this? Well, it's if you have a jump instruction. How do you know if you have a jump instruction? Yep. What's ALU up? Not shown very well. Supposed to be the bits 31, 30, 29, 28, 26. It was better in the. I'm sorry. No, I'm sorry. That's output. It's this right here. It's this blue. There, instruction 31 to 26. That's the opcode field. I got fooled. That's not the opcode field. That's an output. The reds are outputs. The blue is the input. Okay, so there's our jump instruction added, and now we've got the full Monty. There we go. Single cycle processor with data path and control can do any of the instructions, and obviously more could be added. We could add a JR instruction. We could add a JAL instruction. We could add BNE instruction. We could add ADDI instruction. We could add whatever you want. Or, nor. We could add shift instructions. We could add a lot of instructions. How would we add an instruction? What would happen if we said, let's add JR? What does that mean? Well, what did we do to get this far? How did we get that? Step 1, step 2, step 3, step 4, step 5. What was step 1? For the assembly language instruction in the ISA, figure out what the register transfer language equivalent was. What things have to happen at the register level to do that thing? Okay. Can anybody quickly say what the JR instruction does? It takes register 31's value and it puts it into the PC. Yeah, register 31 has to come out of there and it has to go into there, right? Everybody agree? So JR says, don't load the PC with PC plus 4. Don't load the PC with the branch address. Don't load the PC with the pseudo-direct jump address. Load the PC with the value stored in register 31, the return address register. Is that right? Do you agree? Yeah, so therefore we have to make a way on here to implement that new register transfer language instruction. If you like, I'll write it right here. PC gets register 31, if you like. Or write it a different way. It gets register RA. Whatever. Okay? So when you decode the instruction, you say, that's what I have to do. Do we have the ability with this data path to do that? If yes, no changes are needed. If no, changes are needed. I think you can see that some changes are needed. So we have to get it out of here. Is it possible to get register 31 out of here? Well, if we put a 31 here, or if we put a 31 here, or if it was already in those fields, or if we forced in. What about this? Here's one for you. Current value is INSTR 25 to 21 on that bus. What if I just put 11111 on that bus? So whenever I take the top one, I'm putting right here the value 31. That forces this to read the RA register, doesn't it? It doesn't leave it up to chance. Oh, I hope this happens to be 31. You force a 31 right in the door. Great, that would do it, wouldn't it? Now, when would I say, take that top one? On the JRRA instruction. When would I say, take the bottom one? On everything else normal. All right, got it? So one more mux, new value, get it in the door, control it correctly using a brand new control point. So now there's a new control point. Got it? So you add the necessary hardware to allow the register transfer language instructions that you need, and then you add the necessary controls and collect those and make those part of the control structure. So there would be a new control signal coming out of here and going to that mux. Okay. We're just talking theoretically here, but I want to convince everybody this didn't just pot the A. You know, this built up step by step. The steps were 1, 2, 3, 4, 5. And anything you're going to add to this needs to follow those same steps. 1, 2, 3 for data path changes. 4 and 5 for control changes. Right? This is not Hojid Dedi Olur. This came from principles of turning an instruction set architecture into a machine organization. And therefore, any new instructions that you want to add are going to have to follow those same principles to come into the machine organization. Are we okay on that? All right, I'm not going to do it fully now, but we'll get back to that topic later. Let's move on. Now, the next thing to look at is the timing of this. Let's say, how long does it take to do the instructions? Well, we know that the slowest instruction is load word. We've already convinced ourselves that it takes the most. But I'd like to actually go through the exercise here. Oops, got to erase that before we can. I'd like to actually go through the calculation of the instruction timing for each of the categories of instructions that we have. Looks like it's going to be better if I do that. Okay, there we go. All right, what this at the top says, what's the clock cycle time? And how long will our clock be if we assume that mux delay and control unit delay and sign extender and access to the PC and shifting left and wires and setup and hold times are all negligible. Negligible means, cifra salabilir. But we don't assume that the memories are negligible. We don't assume that the ALU and adders are negligible. We don't assume that the register file is negligible. We have timings on those. Let the instruction and data memory access times take 200 picoseconds. Let the ALU and adders take 200 picoseconds. Let our register file access, whether it's a read or a write, take 100 picoseconds. Okay? So we're going to use these times and let these be cipher, right? Because they're small, and this makes the calculation a little more complicated. So if we do that, now we have to figure out, for each type of instruction, R-type, load, store, BEQ, and jump, what steps are needed. Okay? So instruction memory access time we just read is 200. Register read we said is 100. ALU is 200. Data memory is 200. Register write is 100. Right? Those are the numbers that I just copied from there to there. Okay, let's take the first one. R-type instructions. What do they need? Do we need to fetch anything from instruction memory? Yeah, we do. You can't do any instruction unless you fetch. So we got to fetch from instruction memory. Do we need to get anything out of the registers? Do we read anything from registers on R-type instructions? Yeah, we do. Do we do anything in the ALU on R-type instructions? Yeah, of course. In fact, that's their main job, is to add, subtract, or shift, or XOR, or whatever in the ALU. Do we use anything in the data memory on R-type instructions? No, we don't go there. It's not a load or a store. Do we write anything back to the register file? Yeah, we do. So there's another 100. So we both read from register and we write back to register. So the grand total for those would be 600 picoseconds in order to do an ALU instruction, if you could have a clock just long enough for ALU. All right, let's look at the load instruction. How long does the load instruction take? Well, you got to fetch it. That's 200. Do we do any register reads on load instructions? Yeah, you got to get out the RS value. There's 100. Do we use the ALU on load instructions? Yep, got to add it together to get the memory address. Do we go to data memory on the load instructions? Yeah, we read from it, so there's a 200. Do we write anything back into the register file on load instructions? Yep, there's another 100. So the grand total on those is 800 picoseconds. How about the store instructions? What do? Well, they fetch the instruction. And then do they read anything from register? Yeah, part of the address has to come out of the RS field. So we've got to read register. Do we calculate the address in the ALU? Of course, just like we did on those. Do we go to data memory and do anything? Yeah, we write something in. Do we write anything in register file? No, not on stores. Okay, so those take 2, 4, 6, 700 picoseconds. Okay, BEQ. What does the BEQ instruction do? Well, it obviously fetches. Does it need to go to register file to get any operands? Yeah, there's 2 register values. It has to go get those. Does it use them in the ALU in any way? Yeah, it subtracts them. Okay. After that, does it go to data memory? Does it write anything back in there? No, it doesn't. So the grand total there is only 500 picoseconds. Pardon? No, we don't write anything back to the register file on a BEQ. No, we don't change any data values in the register file on a BEQ. I'm sorry. We change the PC, but we do not change anything in the register file. Branches don't change data. Branches don't change data. Yeah, okay. Okay, let's take the jump instruction. Jump instruction does what? Fetches, has to go to instruction memory. Does it get anything out of the register file? Does it? There's no register operands. Does it go to ALU for any purpose? Doesn't go to ALU. There's some adders up in the next instruction calculation, but doesn't actually go to ALU. Now it does say adders take 200 picoseconds here. So in that case, maybe we should put in for here 200. If it depends, it doesn't use ALU, but it uses other adders up in the top. Do we use data memory? No. Do we use register writes? No, it only changes the PC. So having looked at that, we notice something interesting here. As expected, load is our slowest operation. And as expected, if we were a single cycle machine, we would have to have an 800 picosecond clock cycle, and that would waste time, and lots of it, for everybody else. That would waste time for everybody else. In other words, they would finish what they had to do and have a lot of tea drinking time. Oh, that's fine, Hoja, let them drink tea. That's okay, we like tea. But no, that's not an efficient use of our processor. It's not an efficient use of our processor. So you can see that single cycle has advantage and disadvantage. The disadvantage is it uses the clock cycle very inefficiently. It must be timed to accommodate the slowest instruction, which we have just shown. So look at this. In the first cycle, we do a load word. The length of the cycle is 800 picoseconds, let's say. In the second 800 picosecond cycle, we do store word, and we have wasted time, because store word doesn't take 800 picoseconds. So it also may be wasteful of area, because we have functional units that, like adders, that have to be duplicated since they cannot be shared during a clock cycle. So you have to have multiple copies of things, which we saw. But it is simple and easy to understand. So that's why we begin with single cycle machines. Simple and easy to understand. How can we make it faster? Well, let's do that after break. Okay? So catch some oxygen and some liquid and stroll around and come back in 10 minutes.